as an assistant professor. Dr. Dhaked has expertise in various chemoinformatics techniques and computer-aided drug design approaches. He also has experience in the application of DFT and quantum mechanics methods, that is transition state calculation for reactions. Dr. Dhaked will speak on handling of tautomerism in small molecule chemical databases for the redesign of in-situ dating. So I will hand over to Dr. Dhaked. Dr. Dhaked, please. Dr. Dhaked, can you hear me?
Yes, sir, I hear. Can you see my slides, sir?
No, you have to share. You have to share the desktop. Then open the slides.
Yeah, I see the option like. Okay, now you can see, sir.
Yes, we can see now. Please go ahead.
Okay, thank you. Thank you, sir, for giving your kind introduction and giving me this opportunity to present my some of the work what I have been doing since last 4 or 5 years in NCI. Good afternoon, everyone. So, title of my talk is Handling of Tautomerism in Small Molecule Chemical Databases for Redesign of INCI version 2. So, why we are talking about INCI version 2? Currently, we are using INCI version 1 and that solves a lot of problems. So, INCI Trust is planning to come up with new version of INCI that we will be following in the coming years like INCI version 2.
Dr. Dhaked, we are not sure. Yeah.
Oh. Yes, sir. Tautomerism. So, tautomer is a phenomenon by different isomers are in chemical equilibrium to each other by chemical reaction. So, this equilibrium may be very fast and it may be very slow, but in the text flow conducted, usually see these are the isomers which are readily interconvertible with each other. But that is not the case for all times. So, such definitions are ill defined in the literature. So, tautomer is quite sensitive to several environmental factors like pH, solvent, temperature, time, pressure, heat transportation, and storage conditions. So, tautomer is basically very broad term, but here we are going to talk about mainly 3 types of tautomerism: prototropic tautomerism, in-chain tautomerism, valence tautomerism. As name indicates, prototropic tautomer, this is a type of tautomer that involves the migration of the hydrogen from one atom to other heavy atom, along with the reorganization of a single and double bonds. Ring chain tautomer, this is the type of the tautomer that involves ring closing, ring opening along with migration of the hydrogen leading to the cyclic form. And third one is valence tautomerism. That is again one kind of ring chain tautomer, but it does not involve any migration of any group or hydrogen atom. So there is only reorganization of single and double bond. If we compare valence tautomerism with the prototropic tautomerism, there is one common thing both and all the reorganization of single and double bond. And if we compare valence tautomerism with the ring chain tautomerism, you can see there is a ring opening and ring closing between them. And if we compare ring chain with prototropic tautomerism, we can see there is a migration of the proton type of the tautomerism. So why we worry about tautomers in the drug design? There are several factors to directly, indirectly affecting the drug discovery process in different stages, like property calculation. When we are going for QSR related studies, we are going to compute different property like PPA, log, hydrophobicity, etc. by computational tool. But these property for tautomers vary from one molecule to another molecule, so they may affect the final outcome. Similarly, if we are going to design similar or diverse library or we are going to substructure search, these are also affected by because of the presence of tautomers because any motor similarity between tautomers is very low. Structure-based designing method like docking. So tautomers vary from one tautomer to another tautomer. There is a difference in the number of hydrogen bond donor as well as hydrogen bond acceptors. Therefore, these affect in the scoring and binding process. Protein crystallography. What is the correct tautomer form of the ligand in the protein, which is very difficult to determine. If ligand is present quite deeply in the active site. Registration in the databases, in many cases, there is no unique entry for per molecule. Multiple entries are there in the same database as well. Sometimes multiple data inform are present in the multiple different databases. So tautomers in ligand binding interactions. How tautomers behaving in the binding site. So if we have very good resolution, so we can easily detect what are the correct hydrogen position in the molecule. So usually we believe that most stable form of the molecule bind in the active site. But there have been some cases where it has been found that even a minor tautomer or less stable tautomer is binding in the active site. For example, there are some of the barbituric analogs which can exist about 4 or 5 tautomeric form. And here we see there is a equilibrium between tri-keto form and the 1-hydroxy form. And this hydroxy form that is binds in the active site is less stable compared to this form which is more stable in the water by 20 kilocalorie per mole. So this indicates how protein allows the identification of the less stable tautomers because they have better complementary interactions because of this hydrogen migration with increase in the number of the hydrogen bond on a molecule. There are several serine-based molecules which are quite active against the leaching toxins. So out of these 4 tautomers, which tautomer is going to bind with this toxin protein? So here is the tautomer 3 which provide better interaction with the residue of the active site. Therefore, tautomer 3 is less stable bind with the active site. There are several other cases like the pyrazolone derivatives in the CDK4 tautomer has the same occupants in the active site by similar molecules and other kinases have only one tautomer. There are some of the factors like microphage migration, inhibitory factors which catalyze interconversion of the phenyl pyruvates like ketone in all tautomers, and this rate of interconversion is almost same. Therefore, this enzymes have the affinity or specificity for both tautomers. And chlorothalidone is another example of the ring chain tautomerism and is used as a diuretic. And out of these 3 possible tautomers is the electric form which binds in the carbonic anhydrase second enzyme in the active sites. There is one more drug, isoniazid. This is well known drug for the tuberculosis, and this drug interact with the NADP or NAD and make the adduct, and this adduct exists in the tautomeric equilibrium with the ring form. And this ring form is more stable. However, in the actual condition, this adduct in the less stable, it binds with the enzyme leads to the inhibition of the tuberculosis for the target amino acid protein reductase. So in the coming slides, we are going to see different kind of the transforms, different kind of the tautomeric reactions which are present in the chemical literature and some of the software tools. So I have basically classified these rules in the 3 groups: prototropic, ring chain, and valence tautomeric. And where PT indicates prototropic, RC indicates ring chain, and VT indicates valence tautomeric, and further other NN indicates the number of the rules, and if there is an evolution of there is variant is present in the NN. So overall, we have around 80 rules collectively, and we are going to talk about them, how they are present in the different databases, what is their occurrence rates. So before going on those details, these are the set of around 20 rules which can be set as chemoinformatics tool. That is one of chemoinformatics tools we have been using here. So these are different tautomeric reactions which involve different kind of the chemistry for total migration from 1,3 to up to 111 type of the hydrogen migration. And these include simple system like aliphatic amine, aromatic means. Then you have aromatic systems which involve extended hydrogen migration. There are some other special cases like 1,3-none. There are some of the nitronic acid reactions. There is an example for the nitroslo-oxygen tautomers by simple cases as well as by phenyl ring. There are some other systems which involve hydrogen migration by 1,2 hydrogen 6, while others involve the hydrogen migration between all position of the molecule. So how do we represent these chemical reactions in the computer language so we can easily analyze different databases? We represent this chemical reaction in the form of the This mix where one side of this data sign indicates this is the reactant and another side indicates this is the reagent specifically form. That work in bidirectional, so we can start from any side of the reaction. So, in addition to these, what we have seen at this that there are some new rules we have collected from the literature and encoded in the form of a mix. These include different kind of the chemistry, and there are some examples which involve total migration like 1,4 and 1,6 hydrogen 6, and these are mainly N-oxide and hydroxide systems. There are some other systems which are the polycyclic system, which involve the hydrogen migration from the carbon to the carbon. Usually such kind of the migration are not observed, but in the polycyclic system, these systems are more stable compared to the complete aromatic system. There are other also examples which involve proton migration by 1,2 and 1,4 hydrogen ships, which include different kind of the chemistry. There is one example which involves of tautomers through silicon atom. Usually that are not observed in the tautomerism. There are some other examples which involve phosphorus during tautomerization. So next topic is the ring chain tautomerism rules. So these ring chain tautomerism rules are based on basically a type of the nucleophilic center on the electrophilic center. In such a way that it can lead to two kind of the cyclization. If this electrophilic center is becoming a part of the ring, then we call it exocyclic cyclization. If it is out of the ring, then we call it endocyclic cyclization. And what are those different electrophilic systems? Where such reaction can occur via carbonyl, 5-carbonyl, and cyano group. And these are some of the nucleophilic system like OH, SH, primary amino, secondary amino that can involve in the system of the nucleophilic effects. In the 1970s, Baldwin has proposed around 15 rules for ring cyclization of the reactions based on their stereoelectronic features. By considering what is the size of the ring is getting formed from 3 to 7, what is the center where this reaction is closing, whether it's exocyclic or endocyclic, what is the geometry at the carbon center, sp3, sp2, and sp. So based on that, we have given a set of the rules. We have a number for size of 3 to 7. Box shown in the green, which are the favored reactions, and the favored reactions are from the red, and the gray show that these reactions are not reported or those rules are not reported in the literature. Based on similar analogy, our group also developed the ring chain tautomerism rules. We see there is no tautomerism rule that involve any tetrahedral center during tautomerization. Mainly, our rules are coming from the tautomerization, including reaction at the trigonal or diagonal centers. Even the smaller ring system, some of the possibilities are also benign. So these are around 11 rules, which involve different kind of the chemistry like 3-exocyclic. This indicates the 3-membered ring is formed during cyclization, and this is exo kind of the cyclization at the trigonal center. NH group attaching this carbon group will be the 3-membered formation. Similarly, there are some other examples where we are going to make different kind of the different size of the ring system, and these may be like trigonal, diagonal systems. In addition to what we have seen in 11 rules, there are other rules which are not covered about in the previous slide. So we have again encoded them in the form of the rules which involve the different kind of the chemistry what we have not seen in the previous slide. So during ring cyclization, usually there is a total migration by 1,3 hydrogen shift, but there are other cases we will see which involve the total migration by longer distance. Like here we see total migration during ring cyclization by 1,4 hydrogen shift. The other case 1,4 hydrogen shift, 1,5 hydrogen shift. And there is a special case like phosphorus system where we have seen in the previous rules. Here we see the ring cyclization at the phosphorus center. Therefore, we will introduce the chemistry. Similarly, the other example that involves the phosphorus center. In addition to this, there are some other examples which involve the boron during ring cyclization. There are two systems which are involved. There are the rings which involving leading to this ring chain pattern between two component systems. There is another example, boronic acid based boronic acid octoboron ring chain pattern. There is other system which involve the isomerization between two members with one ring system as well as two ring system. And a valence tautomeric, these are the new transforms which were compiled from the literature that central evidence Vincent tautomeric by reorganization of the single and double bonds. There is no migration of atom or functional group. So mainly, what kind of ring form there is 4 member or 5 or 6 members. In some cases, we can see the generation of the deuterand maybe in the open chain form or as a ring form. In one case, the benzene oxide oxygen, we know that there is a ring contraction and expansion within equilibrium. And this is a well-known example tetragonal agile pattern is quite commonly reported in the literature for valence tautomeric. And again, we encoded them in the form of the techniques for easy utilization. Tautomerism and identifiers. For the identification of the tautomer condition, identifiers, so we can easily identify one tautomer from another tautomer. So different set of different publisher or different chemical databases and certificates on different kind of the identifiers with the text molecule. One of which like class registry number, this class registry number is not derived from the structure, so this does not have any information related to the structure. Even it does not have any information regarding tautomer. So it can't take care of the tautomer molecules. So because this is a warfarin well-known molecule in the pharmaceutical field. If we search this molecule in the PsyFinder, we have around 16 examples, 16 number for warfarin. And out of these 16, 7 class registry number belonging to the open chain tautomer, while rest 9 class registry number are referring to the closed form of the molecule. You can see how you can see diversity of the molecule. We were not knowing whether they are tautomer or for people who are using this class number for them, these are the different molecules. So they are the tautomer of each other. INCI or INCI2, this is the INCI or INCI2, this is the IUPAC International Chemical Identifier. This is the most popular identifier in the community, and it has got a layered structure. And these layers have the different information regarding molecule, like name layer have the connectivity information, different charge, stereochemistry, isotope, and fixed hydrogen layers. And it was basically introduced so that it can take care of the tautomers. But actually, this does not take care of all kinds of the tautomers. So therefore, it is a problem in this version. And this is the INCI for this molecule, but as the size of the molecule increases, there is this length of the INCI also increases. So this speed the problem how to show this long string. So people have introduced the INCI key where we have the compact information regarding this INCI. So we can easily use this INCI key for chemical searching in different databases, and we can easily compare whether these two INCI are same or different. So INCI can identify based on the 5 features like fragment, isotope, charge, and tautomer, and stereochemistry. There are possibility of 32 possible variants. Pictures is identified that is sensitive to these 5 features so that it can identify the molecules which have any differences in the fragment, isotope, charge, and tautomer and stereochemistry. Therefore, if we see these set of molecules which are present in zero, they are different, they will have the different identifier, the pictures. Therefore, this picture indicates is sensitive to all 5 features, that's why all 5 features are critical data. Another identifier from these 5 features is the features. And this feature is sensitive to the 4 features, fragment, isotope, charge, and stereochemistry, and this is not sensitive to the tautomers. Therefore, it can easily identify set of the tautomers, and each tautomers will have the same features value. So this is the one of the amino acid histidine, and this can be written at the different forms. Like it can have been the salt form in one database, it may be in tautomeric form, it may be 2 different stereoisomers form based on RNS approaches amino group. This may be the deuteranic form, and if any of the oxygen or nitrogen has got isotope, it may be in the different isolable form. And if database has the error like this, where we see structure valence for nitrogen is not satisfied, we can assess structures in databases. And if the ionic interaction with organic counterpart is not properly handled, we can see there is a covalent bond that is again error. So if we compute the fictus, for fictus as you know, this is essentially the all 5 features, fragment, isotope, tautomers, charge. Therefore, for fictus, these are the different molecules, therefore these all structures have got a different fictus, so they look like the similar structure. And during this computation of the fictus, there is a structure normalization, though this structure has the error, but these two have got the same fictus identifier because the normalization is correct the valency. Similarly, this also corrects the error in the structure, that's why these two structures has got the same fictus. Because as we know, the fictus is sensitive to the sorry, not sensitive to the tautomers. Therefore, these two structures have got the same identifiers. And if we compare to other structures, they look like similar, but they have got a sensitivity to the stereochemistry, charge, isotope. And if we compare their IV is the identifier where the identifier not sensitive to 5 features we have been discussing like tautomer, isomer, charge, isotope, and fragments. Therefore, you can see that all of the structure has got the same identifier, so we can know easily that okay, these are the related structures to each other. Let's see how this standard entity behaves in such cases. This is a standard entity for this molecule, and this can exist in the tautomer form, and therefore these are the tautomers together, and some tautomer definition present in the current version of entity, therefore they have got the same entity. But if we include the other molecules, they are different from each other. And in the case of the butanic structure, because there is a structure normalization, therefore they are the same entity, and other places there is a different entity. So here we are comparing some set of examples how this is standard and non-standard. Standard have the by default some tautomer definition, but non-standard does not have. So it has some definition we have to keep the option on while computing this non-standard to the tautomer. There is one example this can present in the 5 different tautomer forms. If we compare the non-standard entity, you can see all of the tautomer has got a same standard entity, so we know that okay, these are the tautomer of each other, these are not the different molecules. Similarly, if we compare the non-standard entity, we can see that all of them have got the same non-standard entity. This suggests that such for such molecules, tautomer definition presents in the both standard as well as non-standard. So we can say success rate for such kind of molecules 100%. We can easily identify such molecules. There in some cases there only 2 set of molecules have the same identifier, others may have, then we can say there is a partial success rate. There is another example that can exist in the atomic equilibrium by one side, which is called Tautomerism, where if we compare the standard tautomer 1 to tautomer 2, they are different from each other. So this thing is such tautomer definition not present in the current version of the standard entity. But if we compare the non-standard entity identifier, we can see easily that okay, they have got the same identifier, and this is where they are the tautomer of each other, and tautomer definition for such molecule is present in the non-standard entity. So therefore, entity success rate for non-standard entity 100%, for the standard entity is 0%. This is another example for oxygen nitroso via phenol. And here we see neither standard entity nor non-standard entity for both tautomers. So therefore, we can't take care of such molecules. Therefore, they seem to be different molecules of the tautomer. So it is very problematic to know whether they are tautomer or different molecules. So we have collected a set of around 86 rules, and we have analyzed the appearance rates across different databases. And we have given careful different data people like drug bank, ligand, and the structural database on the organic part, Campbell, which is the collection of the several activities, Enumeration extension for shared camera patent database collected from the description of and Cam Navigator and chemical structure databases like the code database. These all 9 databases will be around 400 million structures. So we can analyze 400 million structures for each individual goals to see what is the appearance of each individual goal database. Here if we see these two rules like rule number 2 to 12, these have got a very high occurrence rate and each of them has got at least 3 million exam percent databases. In addition to the rule number 16 data also has got a number in the million. And this indicates these rules are quite common which are being involved. And if you go down in this table, you see these numbers, there are also numbers, you see some examples for these other rules too. But if you see their increase success rate, you predict whether they are very identified their related success for Tautomer based on stability or non-stability, which is quite varying. Like for role 2, we see that the increase success rate is around 6%, for next role it is around 0, for rule number 5, it is around 99%, so it's quite varying. This honor average here we see around 32% success rate is placed to identify whether the molecule are the Tautomer or the not. And if we go down in this table here, we see this is again quite low and some cases is quite close to 0 or some percent. But if we compare with the non-human, their success rate is improved significantly compared to this. And especially in this panel, we see success is better because non-human definition involves that for the extended kind of the identity. Therefore, we have the better success rate for the molecule. These are the new transforms from rule number 20 to the rule number 49, and here we see again appearance of these different rules. For 2 rules, we have numbers and ligands, for others, we have numbers and 2,000 and 300. And first, we have got examples of different databases. As we see the increase success rate, here we see most of the cases we don't see increase success rate here, less than 1%. This indicates the such Tautomer definitions and such rules is not present in the current version of it. If Tautomers are present for such molecules, we want to be able to identify whether these are the Tautomer of each other or not. These are the statistics for ring chain and valence Tautomer examples. I have highlighted the 2 rules, rule number 3 and 4. These are the rules which are related to the ring chain Tautomer of the pentose and related compounds. So these has got a numbers in the millions, others we have quite varying numbers. And similarly for valence Tautomer, rule number 2, which is not factorial like that Tautomer is numbers in the millions. As we see their increase success rate, no matter whether it is like standard or not standard increase. Here we can see their increase success rate is almost 0 of increase. So this again indicates there is no definition for such type of the example. So there is a need for increase again too. So far, what we have seen the average life, we have analyzed the increase success rate and their appearance for rule guide. But here again, we calculate that with all things again, like all set of the rules, we apply all set of the rules on single molecule and we see whether all the method Tautomer will have the same increase or not. We are quite positive that for few rules, there may be same increase, for others it may be different, and if we basically want to be able to completely calculate. Based on this quite complex calculation of this table, here we have overall increase recapitulation, as you can see, overall increase success rate. On average, we have around 66% increase success rate. Overall increase success rate means we are including a complete pass, means all Tautomers have the same increase. As they have partial pass, means some Tautomers have the same increase, others have the different. So including all, we have the average around 56% success rate. But if we consider on the case which in that case, only all Tautomers have the same increase, and you see that number that is quite close, around 15%. Like complete pass, means all Tautomers will have the same increase. That is quite low and quite very small. If we see overall Tautomer potential of these databases, we are quite varying from 47 to the 80%, and around on an average it will be around 17%. Which is more quite Tautomer information in these databases has very high potential for Tautomer. Based on this rule, we have developed Tautomer innovation tool and the interest and some research whether this might be interesting for the Tautomer. Again, they can also embed the structure of different research. Here are some of the options. By using single step, we are going to apply the D3 on single time, multiple steps. In that case, we apply the rule again and again until the Tautomer there are some other customized options which were all of the rules for new rules. And if you have got some new examples, they can write your honestly and straight how to be able to generate and here is one example that is associated with the all kind of the pattern level, prototropic, link chain, and valence pattern. So by prototropic pattern is in the side chain by keeping or generating this pattern, and if there is a link chain pattern between this coronic and this carbon something side chain splitting this link chain pattern by coronic acid, osteoporose rule, and if there is a link closing of this hydrogen at the cytidine nitrogen center, formation of this valence pattern. So here we can see again the tendency of this all tautomer is different, so we don't know whether these are different policies or other tautomer is basically the need of development of new version of the species. Next topic is tautomer conflicts. What are the tautomer conflicts or tautomer conflicts? These are the sort of molecules that present in the same databases or in different databases which are tautomer of each other. So we have analyzed around 40 different databases collected from different sources. Some of the results are on our list. Let market select databases UNESCO the building blocks in the streaming molecules. So we have found around 31 tautomer conflicts affecting around 63,000 molecules. And mostly these tautomer conflicts are coming from the two tautomer pairs. And if we go down, these tautomer conflicts are there. Mainly, and then the tautomer structures. Here is the example where we can see different tautomers of the same molecule are sold at a different prices. Here we can see the price for 1 gram is $31, and for the another tautomer price is $51. Here we have analyzed a percent database which has around 100 million molecules, and here we found around half million of the concentration around 1 million molecules. And mostly these conflicts are coming from the two tautomer pair, and we have analyzed up to 25 tautomer conflicts are present in the percent databases. Similarly, we have analyzed the ligand part of the protein data bank, and we have found there are 100 tautomer conflicts. For example, uric acid, this is the clearing byproduct, and this molecule in hydroxyl form is present in the B2PDB, while this in keto form is present in the 15PDB. Specialty phosphate is one of the metabolites and on several metabolic pathways in all organisms. And this molecule in the hydroxyl form present in around 51 PDB, while in the keto form it is present in 31 PDB. Maybe we have found one example is present the 4 tautomer form, and each of these tautomers is at least 2 different PDB added. So this indicates how these tautomers have different systems and different proteins. So here is a list of the tautomer conflicts that we have seen around 31,000 market select we have categorized based on the rules. So these are the examples we have found for tautomer conflict 4 individual rules. And out of these we have selected for testing on 24. And we found that out of them, these are indicated these are the tautomer conflicts by experimentally. So these are some examples where we found that will indicate that we have got a same structure for the core tautomer, so when the indicate that these are the different molecules. That is when we tested for the NMR extra and the mass structure, we found that we have got the same structure, they are converted to the same tautomer. Only red portion became in these cases we have the different structure or different tautomers. Similarly, for the found example of Vincent tautomer in the most of the cases, the CD region is here, we are the same molecule. In a few cases, we have found that different red color structure that indicates we are the 2 different tautomers. So, how do we know why this rule these are interconverting features? In order to understand that we have to make network, we have to make all possible tautomer identity, and then we look for the what is the shortest path. So by using this molecule 1, we can get all possible tautomers. We have got around 12 different tautomers. And these are 2 different tautomers which are present in databases. So now we are looking what are the different parts. These 12 different tautomers are interconnected by combination of the different rules. So structure one step that is 7 by 1 step, and if you go by this part, you can see this another 2 step or 2 rules. If you go by this again 2 step, and if you go by alternative rules, you can go by multiple steps to reach that step. So this is the rule 7 by which these two structures can interconnect by a single step. And if you want to go to this by different alternative pathway, like if you want to go in this pathway, you can see first we have to apply the number 2, then it's number 2, then we'll apply the number 6, then it's structure number 3, then we'll apply the number 7, then it's structure number 9, if we are finally applying the number 2, then it's 7. So rather than going this long pathway, it will be easier to go by road number 7 only, because only one time we are using this road to enter our time. So this is another example that Tautomer can be from different databases. So this 1-phenyl-3-methyl-4-benzyl thiazolidine is a molecule, and it is used in the lipid membrane for the extraction or removal of different metal ions. Efficacy for selecting for different metal ions depend on the particle correct atom form of this molecule in the lipid membrane, and this measure atom form depend on the solvent as well as the concentration of the molecule. So this molecule can present these 7 different tautomeric forms. Out of these 7, 5 are affected directly and indirectly by the chemistry of the atom or bond. Like that, here you can see there are 2 possibilities of either item. And these 3 tautomers here, there are no possibilities of the so much. It will need more numbers for these molecules. And if you see the database, like only 3 molecules have got the Prasad V number, and others have not got so far. And if you see for this transmission number, there are around 49 references available in the literature, and this is a molecule that body is around 859 references in the literature. And for this molecule, we have only 2 references, because there is no interlink between this idea about the different references. So we have analyzed different databases where these are different tautomers present in the different chemical databases. We found that this is structure number 1 or tautomer present in the 12 databases, and this is structure without defining the chemochemistry present in the 16 databases, and this chemochemistry defined if it is R, then it is present in the 3 databases, it is chemochemistry S, it is present in the 2 databases, and this is present in 6 databases, and this molecule present in the without chemochemistry. Molecules are not present in any of the databases. And what are those different databases? This is the full list of the databases where these different tautomers are present. Here we can actually see that these 12 different databases where these molecules present. And these are the 16 different databases where this molecule of tautomer is present. And if we compare that, like chemistry, same databases which has defined stereochemistry, and some other tautomers do no stereochemistry, these are the same databases, which is problematic. There is no interconnection between them. In conclusion, we can say that based on our rule, there are 70% probability that these molecules are potential for tautomerism or for high tautomerism. And we see there is standard entry or non-entry success rate for identifying whether 2 molecules are tautomer of each other or not. It is quite low. In the case of standard entry, it takes around 50% of the cases. And if we see the non-standard entry, then success rate is around almost compared to the standard entry. And the tautomer is predict all possible tautomer of a given molecule based on the smart matching. And this indicates the current version of entry deployed in the 2004 shows that it takes care of around 20% of the work due to the urgently the development of the entry version 2. So whatever strategic reaction we have proposed to the entry trust, and they are carefully looking at them, and we believe that the incoming intelligent will be part of, so that there will be no such problem to identify such molecules, whether they are tautomer or different molecules or conflicts. Thank you everyone for joining me, and thank you to the organizer around this opportunity to present my work. I would like to thank you to my participants supervisor. I have been with them at different time. Mark Nicholas, I was with him in the NCI. This was the software developer who was helping us during our problems. Professor Dr. Prasad, I was with her in Kothari fellowship. Dr. Bharatam, Mohali, I was with him during my PhD. I learned with him application of quantum chemical science. And my master supervisor, Dr. I was with him during my master, and I learned this at the time. Thank you, everyone.
Thank you, Dr. Devendra. Very nice presentation, concise and clear. I don't see any question from the participants. So, thank you.
Thank you, sir.
Yeah. Thank you. And
shall I disconnect?
yeah, now it is okay.
Okay.
Thank you, Devendra.
Thank you, sir.
Now, the next speaker is Dr. Ramesh.
Hi, can you hear me?
Yeah, we can hear you, sir. Okay. Let me introduce the speaker.
Please go ahead.
So Dr. Ramesh got his PhD from IIT Madras in computational condensed matter physics. He then changed course and moved to the field of computational biophysics for his postdoctoral research at the Molecular Biophysics Unit, Bengaluru. He then joined the Origin Discovery Technologies in 2004 as a molecular modeler and went on to play a key role in the structure-based drug design group as a modeler and a crystallographer. In 2010, he joined the Biocon BMS R&D Center at Single International UK and established the CAD group there. He led the CAD group with several impactful contributions in various drug discovery programs till June of 2020. Recently, he has founded Think Molecular Technologies, a molecular formulations company at Bengaluru, which aims to partner with biotech and pharma companies, bring greater efficiency to drug discovery and molecular formulations. Now, I invite Dr. Ramesh to give the talk. He is going to speak on CAD in drug discovery, choice of tools with case studies. Dr. Ramesh, please.
Can I share my screen?
Yes, I have to share the screen by if you see the tab File, Edit, Share, you can share with it. Otherwise, you can simply click on Share the desktop.
Yeah, actually that's disabled. That